Hey guys, Gajansky here, and we're going to talk today about monosaccharides and their relationship to disaccharides also. So we're going to start out by looking at three of the most common monosaccharides that we need to know about, and those are glucose, galactose, and fructose that you can see here. So if you remember from before, looking at glucose, when you look at the ring of glucose, you should be able to number the carbons around the ring. So glucose has 5 carbons that are found in the ring, and then there's 1 carbon that hangs up off the ring. So if you number these, you go clockwise around this ring, and there's carbon number 1, 2, 3, 4, 5, and finally carbon number 6 that's hanging up off the ring. Now the important thing about identifying glucose is this hexagonal ring structure along with the hydroxyls and the pattern of hydroxyls that you'll see. So the hydroxyl pattern is like this. It's down below the ring, down, up above the ring, and then down again. So it's down, down, up, down. And if you look at that, you'll recognize that this is what's called alpha glucose. So we're actually looking here at the alpha version of glucose. The reason for that is this hydroxyl on carbon number 1. So that's the really important hydroxyl that identifies this as an alpha glucose. If you took that hydroxyl and exchanged it with this hydrogen's position, so we switch these around, that would now form what's called beta glucose. And the beta version is a very tough thing for your body to digest. So beta versions of things are not easy to break apart. It may not seem like a very big difference, but it is. All biological molecules work based on their shape, so their structure. It's really very similar to a key. So if you took all these valleys and peaks on a key, it'll be unique to that key, and that key does what it does because of that shape. You can imagine that if I just filed off one of these peaks, that this key would no longer work. And that's exactly how biological molecules work. They depend on their shape. So even a small change in shape is going to have a very significant impact on that molecule's ability to do what it's supposed to do. So that's glucose. Now if we look over here at galactose, if you look at galactose, at first it seems really similar to glucose, and it actually is, but it does have one really important difference. So if we kind of go around the ring, we'll notice that it still is a hexagon shape, so it's a 5 carbon ring, 6-sided, and if you number the carbons, it's not a lot different from the glucose molecule. It's got 1, 2, 3, 4, 5 carbons in the ring, and then the 6th carbon is up and off the ring. Remember, the important thing is looking at the pattern of hydroxyls. So if we look at that on this galactose, you'll notice the pattern is down, down, up, and up. So in this case, it is this hydroxyl on carbon number 4 that is up above the ring that makes this galactose. So again, it's a very subtle difference. The difference between glucose and galactose is simply the position of that one hydroxyl, and it's very small. But again, like a key, one little change makes a big difference, and that's why galactose is a totally different sugar. Now, over here we have fructose, and if you look at fructose, you'll notice right away, first of all, that the shape is quite different. It's only a 5-sided ring. But if you count up the carbons and look around the ring, you'll notice that it still has the same number of carbons as these other 2 sugars of glucose and galactose. So we have here carbon 1, 2, 3, 4, 5, and 6 up here. But the big difference is that carbons 1 and 6 are actually outside of the ring structure of fructose. So you might notice now, though, that these sugars all have one thing in common, and that is their formula. The formula of all of these is the same. It's C6H12O6. So again, maintain that 1 to 2 to 1 ratio of carbon to hydrogen to oxygen. And that's very important. When you have a bunch of different molecules that all have the same chemical formula, those are what are called isomers. So in this case, these are called structural isomers. In other words, they have the same formula, so you can't tell them apart by looking at that, but they have different structures. The shape of each molecule is unique to that molecule, and that's what defines it as that particular sugar. So those are structural isomers. Now let's take a look at a 4th monosaccharide that's quite important, and that is something called ribose. Now in ribose, if you look at that one, you'll notice at first glance it seems to look a lot like fructose. The shape is a pentagon shape, so it's a five-sided ring. But if you look very carefully and actually count up the carbons, you'll notice one very important difference. In this case, ribose only has 5 carbons. So it has a formula that is C5H10O5. So it still maintains that 1 to 2 to 1 ratio of carbon, hydrogen, and oxygen. And ribose is an important sugar. We'll talk about it later when we look at RNA. And it has a cousin molecule called deoxyribose, which is important in DNA. Now, if we take a look at the disaccharides, so we want to take a look at the double sugars. And because they're made of 2 units put together, there are 2 monosaccharide units joined together, you'll notice that all of these disaccharides in these pictures here have those 2 units. The common disaccharides we're going to look at are sucrose, which we've probably all heard of, lactose, which is a very common sugar, and maltose, which is a little bit less common than the other 2, and we probably haven't heard of that one very much. But all these have one thing in common. They're made of 2 units put together. And in this case, they also have the fact in common that they all have glucose as one of those units that they're made of. Disaccharides have the same function as a monosaccharide. They're used for immediate energy. So when you consume sucrose or lactose or maltose, it goes through your body and your body will digest them, which means it'll break this bond in the middle between the 2 of them, and it will release these monosaccharide units, which we can then use for energy purposes. The general formula of these is a little bit unusual. If you look at it, you would think, since they're 2 monosaccharides put together, that they'd simply be double that formula, but actually they're not. They're a little bit less than that. So you'll notice it's C12H22O11. So let's take a look at the disaccharides and where they come from and what they look like. So sucrose is the most common one. It's glucose and fructose put together. This is usually we get it from sugar cane, so that's what sugar cane looks like right there. You can actually buy that in stores and you can chew on it and it's really sweet. But we normally call this just table sugar instead of sucrose. So that white stuff that you eat pretty much every day of your life, that is sucrose. If you actually go to India, they sell these sugar canes on the street and they grind them up and they spread the juice, which is a kind of a green color, onto shaved ice. And you get this delicious green, sweet Indian Slurpee thing. Now, lactose is a sugar that we probably have heard of before as well. It's made of glucose and galactose, and you might notice that it's actually made of the beta forms. And remember, the beta form is much harder to digest, which means that a lot of people have trouble breaking this bond between these 2 monosaccharides and then getting energy out of this molecule. Lactose comes from milk, so it's the dairy sugar. And kind of an interesting thing about lactose is that humans actually only evolved to be able to digest this about 8,000 years ago. And that happened in northern Africa and spread to Europe. And so that's why in those areas of the world, people generally don't have trouble with digesting lactose. They produce an enzyme called lactase. But when you travel to Eastern countries, like in East Asia, they have quite a bit of trouble digesting the lactose. The final disaccharide we're going to look at is maltose. And maltose is glucose and glucose put together, and this is what it would look like if it were a molecule. It comes from grain starches, so wheat, barley, rice, things like that. And so when you eat these, your body will break apart these 2 units and liberate the glucose, and you can use that for energy. So I have here some delicious beet and sweet potato chips. They're tasty starch, and I'll eat those, but no Mike Myers dressed in a big Scottish guy outfit. I will not share them with you, and I will not get in your belly. That's good. So I hope this helped you understand disaccharides and monosaccharides.